channel. Today we will start with the second chapter, Electrostatic Potential and Capacitance. So in today's session we will see the basic concepts regarding the potential, how you can understand the potential, so based on the grade 11 chapters, and then the capacitance. In that we will study about the capacitors, some derivations based on the series connection, parallel connection, its energy stored, so on and so forth. So today's class we will go with the electrostatic potential. So when we studied about the work energy concept in grade 11 and also the potential energy, kinetic energy concept, we studied about the law of conservation of energy and also the conservative forces. What are these conservative forces? Those are the forces which depend only on the initial and the final position. So you have this potential energy and kinetic energy. So when you consider this as a whole, or sum of this potential energy and kinetic energy, that will remain the same. So we have a derivation of mechanical energy concept. So you had to consider three different positions, A, B, C. In that, find out the potential energy, kinetic energy each step, and then say that their total energy remains the same. That was the law of conservation of mechanical energy. So you have to convert this potential energy to kinetic energy. In that point of time, you will not give any extra work or extra force. So it is just that the conversion of potential energy to the kinetic energy. No extra energy is supplied here. That is why the whole energy is conserved in the system. In the same way, when we consider this electrostatic potential, it is same as this concept. You have to consider one charge Q. Let us name it as test charge. Let me take plus Q. You have to bring this plus Q to this, near this charge, plus capital Q. So where we say that it is placed at the origin and this is at the point R. Point O and point R, both are positive in nature. You have repulsive force. So first you have only this charge. You have to bring this charge from some other point to this point. So now, based on this plus sign, the electric field E is in this direction, from O to R. So now, when you are taking or when you are bringing this test charge from point R to point O, you have repulsive force coming into picture. So you have to do some amount of energy work to bring this charge to this point O. So that gives the concept of potential energy. After potential energy, you have potential difference. So we have to specify the term electrostatic because we are considering with the dealing with the charges and it is at rest. So it is electrostatic potential energy. So when you bring this charge Q, say that you reach some point P. Now you have some extra energy stored here, plus Q in this test charge. That amount of work what you are giving to this charge Q is called as electrostatic potential energy. Okay. So now in this concept we have some 2 points to discuss here. So this is called as test charge. So first thing we can tell as this test charge is so small that it is not that much disturbed by this plus Q. We are considering, we say that it is infinitesimally small. So it is so small, maybe delta Q tending to 0. So it is not disturbed by this charge which is placed at the origin. This is one point that you can just consider from this diagram. You can take this as negative and negative also. So you have repulsive force. If one is positive, one is negative, no need to do any amount of work. It is just an attractive force. So when you have the same charges or the like charges which will repel each other, then you have the concept of work done. So that is the first point. Plus Q is so small that it is not disturbed by this charge which is placed at the origin. The second point is that the direction of electric field. So Fe or the force will be equal to minus F external. This F external means it is a force which you apply on this test charge to bring this to this point. So it is opposite, equal and opposite. Fe is in this direction and the force or the work done is in the opposite direction. So it is in this way. Fe is equal to minus F external. So when you have the force here, you can calculate the work done. So we have studied in the work energy chapter, the equation for work is force into displacement. It is actually F dot S, dot product or the scalar product. So in the same way, when you have the force here as F external or Fe or the electric force, then you can apply this same formula in order to find out the work done. So work done will be equal to, or the total amount of work done you can say. If you have some dr distance, dr in the sense very small. So in total you can integrate this one as Fe dot dr. So this Fe is also equal to minus F external. So you can also write it as minus F external dot dr. So this gives the total work done. This is one and the same Fe, but see that you have negative sign here. Fe is equal to minus F external. So this, now the amount of work done to bring the test charge from one point to another is called as electrostatic potential energy. Now say that you have 2 points plus Q at the origin. This is test charge which is located at R. This is the direction of the electric field E. You have intermediate point P. Now what you do first? Bring it here. Bring this plus Q to the point P and then from P to Q. So we have to now calculate the total amount of work done. We can write the energy as WRP, the total work done. It is nothing but the difference in the potential from here and here. Okay, so I can write it as UP minus UR. Just here if I consider, what is the potential here? What is the potential here? So as you bring near, the potential will be more and more because of this one. So it is UP minus UR. UP is nothing but electrostatic potential minus UR. So total, this is the difference. So the amount of work done from here to here is written as WRP. So this is now called as the electrostatic potential difference. Electrostatic potential difference. It is nothing but the work done in bringing the charge from one point to another point. So this is called as electrostatic potential difference. Now once you know this electrostatic potential difference, we can then calculate the electrostatic potential. Electrostatic potential and then the electrostatic potential difference. So now if you see this one, this equation if you see, WRP as UP minus UR. Now this is nothing but the conservative force. This depends only on the initial position and the final position. It will not depend on the path taken. How you bring the charge, that is not considered at all. So you have to just see the initial position and the final position. So this is the one of the concepts that you can remember here. Okay, under the electrostatic potential difference, you have just the net difference, that is the initial position and the final position. Another point is that you can add any constants here to this potential, any constants. It is independent of the constant terms which you can add here. Plus alpha and plus alpha, if you add here, there will not be any difference at all in between. So it is just the values of this potential that gives the electrostatic potential difference. So this is the concept. Next we will go on to electrostatic potential. So until now we have studied about the potential energy, electrostatic potential energy and electrostatic potential difference. So now electrostatic potential, which we represent with the letter V. Which we represent with the letter V. So basically it is given by W by Q. It is given by W by Q, or work done per unit charge. So now when I discuss about this electrostatic potential energy, I can also take it as this UP minus UR concept as WRP. If I want to define it exactly, I can take this at the position infinity from any point, or in specific if I tell I want to bring the test charge from infinity to the point P. That will give you the clear more definition. So usually we consider the potential at infinity to be 0. So it is UP minus U0. So it is given in your textbook also, UP minus U0, U infinity, but U infinity we usually take it as 0. So in the same concept when we use here, so electrostatic potential is the ratio of work done to the charge Q. How much amount of work you are doing per unit charge. So this is nothing but the electrostatic potential. So when you have this electrostatic potential, how can I write the equation if I consider those 2 points P and R? So it is Vp minus Vr will be equal to WRP divided by Q. WRP divided by Q. I can write this as test charge also. If I want to consider test charge, you can write it as Q. Usually we write test charge as small q. So Vp minus Vr. So it is nothing but, what is WRP? It is UP minus UR divided by Q. That will give you Vp minus Vr. Vp minus Vr. So it is Vp minus Vr. 2 points if I consider the same concept. So you can write it as UP minus UR divided by Q. This is the equation for electrostatic potential. Equation for the electrostatic potential. So it is the work done in bringing the point charge from infinity to any other point. So that is the electrostatic potential. Now we will see what is the electrostatic potential due to a point charge. We do have so many derivations in this chapter. So it is electrostatic potential due to a point charge. This is a simple one. So in order to find that, consider this figure. Plus Q at the origin. You have point P and then say point P dash, and then this is at infinity. Okay. So this is at a distance of r. This is r dash. Let this be delta r dash. Place 1 coulomb at this point, plus 1 coulomb. Unit positive charge. Find out the electrostatic potential. So now when you consider this electrostatic potential, so we just write it as V. V is equal to W by Q, work done. Work done is nothing but force. So I just have to find out this force formula again. So for unit positive charge, one is plus Q, another one is plus 1. So Q1 and Q2, F is equal to 1 by 4 pi epsilon naught, Q1 Q2 by R square. So in the same way, I can now write it as 1 by 4 pi epsilon naught, or instead of this V, we will write it as W as 1 by 4 pi epsilon naught Q into 1. Okay. If I want to bring the positive charge, unit positive charge from infinity to here first, then from here to here, and then to the origin. So we are just considering two different points here, so that at the end we can have the total electrostatic potential at the point P. So from infinity to the point P dash, where we place or where we bring unit positive charge. So it is Q into 1 divided by R dash square into R dash cap. So this is when you bring this up to here, from infinity to this point. The distance is R dash. Now what you do is, from here again bring this much closer. So from when you consider this plus Q which is placed at O, this will be R, this is R dash, and this is delta R dash. So R dash plus delta R dash amount of distance you have here. So work done is 1 by 4 pi epsilon naught Q into 1 divided by R dash square into R dash cap. Now we need to integrate this. So as I have already told you, this will be negative in sign. Why? Because the electric field is in this direction, but you are doing work in the opposite direction. So work done in total will be negative. So when we consider this R dash from infinity to R dash is equal to R. So work done, R dash is equal to infinity to R dash is equal to R. From infinity to this position, we are calculating this at point P. So the total distance from infinity to R, from infinity to the point R, that is what we have to calculate now. So work done will be minus from infinity to R, Q by 4 pi epsilon naught R square into dr, or you can write it as R dash square into dr. Okay. Since we are considering a dash, you can consider dash here also. So W is equal to, I will just write it here, W is equal to minus integral of infinity to R Q by 4 pi epsilon naught R dash square into dr dash. Just integrate this one. W will be equal to minus infinity to R Q by 4 pi epsilon naught. I will take this outside. Q by 4 pi epsilon naught integral of infinity to R 1 by R dash square into dr dash. Use the integration formula, the general formula. Integration of R to the power of n dr will be equal to R to the power of n plus 1 divided by n plus 1. In the same way, you have here R dash square. When it goes to the numerator, it is R dash raised to the power minus 2. Minus 2 plus 1 is minus 1. So you have W as minus Q by 4 pi epsilon naught into minus 1 by R dash from the limit infinity to R. So W will be equal to, minus into minus will be plus, Q by 4 pi epsilon naught into 1 by R minus 1 by infinity. 1 by infinity will be 0. So I hope I will erase this one. So W will be equal to Q by 4 pi epsilon naught into 1 by R minus 1 by 0. So this is the work done. By the definition, the potential P due to the charge Q will be equal to V. So when we write this work done, in order to bring the test charge or any charge, unit positive charge we consider here, from infinity to the point, to any point is taken as what? V, or the electrostatic potential. It is nothing but 1 by 4 pi epsilon naught into Q by R. This is the equation for electrostatic potential. So it is Q by 4 pi epsilon naught. So just see that V is inversely proportional to R, but electric field is inversely proportional to R square. So very important graph we have here. So inference or the variation of electric field and potential with the distance. So you can have the combined graph. So I'll erase this one. Just keep in mind 1 by 4 pi epsilon naught into Q by R. Variation of at infinity we take the potential to be 0. So you have here E or V. E or V. Now when I express this V, it will be like this. This is for V. This color will be for V. And when we have this electric field, it will be in this manner. So this is the variation, and see that this V is inversely proportional to R and this electric field is inversely proportional to R square. This is, you have to just keep in mind, and this is the variation. So we cannot mention here, I will not mention it. This just V and E, electrostatic potential and electrostatic field. So these are the variations, potential and electrostatic field. So very important graph for multiple choice or any assertion reasoning. Okay. And also to draw the graph, variation of electric field or electrostatic potential with the distance. So in the next session we will see the electrostatic potential with the due to a dipole and other derivations. So after this you have the example numerical in your textbook. So just go through that. It is based on this electrostatic potential. So first you have to find out this electrostatic potential. Calculate the potential at a point P due to a charge of 4 into 10 to the power minus 7 located at 9 cm. So it is a simple one. The example numerical after this derivation. So you have to find out the electrostatic potential. V you have to find out. Just the direct formula which we have derived. So Q by 4 pi epsilon naught into R. So that is what you have to use. 1 by 4 pi epsilon naught. Q is given as 4 into 10 raised to minus 7 divided by 9 into 10 to the power minus 2. You no need to square here because the equation is 1 by 4 pi epsilon naught q by r. So first write the equation and then substitute. So this is the first part in that question. And second part, you have to then find out the work done in bringing the charge 2 into 10 raised to minus 9 coulomb from infinity to that point P. So once you have found out this V, then you can find out this work done, because we know V is equal to W by Q. So W will be what? W will be equal to V into Q. So be careful with the calculation of V, so that you are using this here. So find out what value you get here, substitute in this V and then multiply with the 2 into 10 raised to minus 9. So does the answer depend on the path along which the charge is brought? No, it is not dependent on the path taken. So it is only dependent on the initial and the final position. So this is the concept or the basic concepts regarding potential, potential difference and electrostatic potential energy. Then using that, how to find out the electrostatic potential due to a point charge. Single point you consider and then test charge or unit positive charge, bring it from infinity to one point, then do the integration from r is equal to r dash is equal to infinity to r dash is equal to r. So use the integration formula and then substitute the limits, then you get the equation, okay, and then the numerical. Thank you.